So last time we were talking about braids and braid groups, and this time we're going to talk about something categorical related to braids, namely about braid monoidal categories. So let's go there slowly. So maybe how do you feel about such words as a symmetric monoidal category? Yeah, like you heard it, but maybe you didn't want to. Or
this is exactly the way to play it.
And now you're going to hear it again. so let me start slowly just further with what might be a monoidal category. The idea is that we want to have a category with some associative multiplication, such as, for example, if you take the category of sets, then we can take the product of two sets, a Cartesian product, and it's actually a functor. So what we would like to have a category C together with a multiplication with a product, which is supposed to be a functor. So it's quite often denoted by tensor product, even though in reality it might not be tensor product. So this is supposed to be a functor. And now we want this product to be sort of associative. There is one thing that one can write, which is somehow associative on the nose. So this might be a definition, very strict. Monoidal category. What is a category? C with an associative functor and monoidal, it derives from monoid, so there should be also a unit. So, and with an object 1 in C, such that its product with anybody from either side is equal to anybody. Such that 1 tensor A is equal to A tensor 1 is equal to A for any object. Now, the problem is that those obvious examples that one would try so like the category, say for vector spaces, if I'm using this notation, let's take the category of vector spaces over your preferred field, whichever field you want. Then we certainly do have tensor product of two vector spaces, and that's a functor. Is indeed a functor going from vector spaces times vector spaces. What functor involves that we can, I know it's elementary, but still it's good to just to say explicitly. It involves that we can take the tensor product of two objects, but we can also take tensor product of two morphisms. Being a functor means really that. Unfortunately, it's not really, strictly speaking, associative. So if you write something like V tensor, or okay, U tensor, V tensor, W, and if you go into this really definition of what this nonsense means, then sure, it's canonically isomorphic to U tensor V tensor W, but it's not really equal. By construction, construction will not tell us this is the same object, so we cannot really say that it's equal. Even though it's canonically isomorphic, so everybody would just identify it, and it's perfectly fine to identify it, just it doesn't really satisfy this definition.
Can I, in principle, can change the category, like mod out by some equivalence?
Yeah, so one can replace this category of vector spaces with some bigger category where this becomes truly associative. But then is it really worth replacing those good old vector spaces with some bigger category? I don't think so. So, okay, but this sounds like a nitpicking. Also, say the unit object would be, I guess I should say, it is vector fields over some field K. One would be just the field. But still, it's not really true that K tensor V is equal to V. It's certainly very canonically isomorphic, but the construction is not that. Because the construction of this is like all those pairs modulo some relation, so it's just some strange set in some sense. And this sounds, first of all, incomprehensible. Like, why would ever, okay, they are not equal, but they are so much canonically isomorphic that they are basically equal. So it's like a nitpicking, but we're actually going to use this nitpicking. So that's the reason why I want to write a true definition of a monoidal category. So definition a monoidal category. Well, what is it? Is again a category C, a functor from C times C to C, an object, the same thingy, 1, which is in C. But now you see, we don't really want these things to be equal, but we want them to be canonically isomorphic. This means that this isomorphism is going to be part of the definition. Definition is somewhat longy, but we're going to actually need it in some sense. And a natural isomorphism. So for any A, B, C who are objects of C, we want to have an isomorphism between A, B, C, and A, B, C. I already, at this early stage, stopped writing those tensor products so that you get used to it, because I'm just too lazy to write them all the time. But it's, I mean to write it there, but then I just don't. Okay, so we want to have a natural isomorphism denoted gamma A, B, C. What does it mean, a natural isomorphism? Natural isomorphism should be between functors. So what functors? It depends on which way we find it more comprehensible, whether in this way or in this functor way. You see, when you take C times C times C, you can go in two ways into C. Either first taking the product here and only then take the product there. It's like what we do here is the first functor. Or taking first the product here and only after doing the product there. So it's this parenthesization of the product. So there are two functors here. And this gamma thingy is an isomorphism between these two functors. Which just means that we have isomorphisms between these objects and which are somehow compatible with the morphisms. That's the only thing. So we want this to be natural isomorphism, but we also want this natural isomorphism to be so natural that we can totally ignore it. So what is this condition? And so such that so what is now a problem? You see, if we start applying these rebracketings, so for any kind of elementary rebracketing, we can use this gamma. We can go around some cycle. We can just go along and return home. And we demand that we get the identity. So let me write it down explicitly. Let's start now with 4 objects. So when you take A, B, C, D, I will keep this order because I cannot change order using those gammas. Gammas don't change order, they only change some parenthesization. So let me always keep this order. But there are now several ways how to put their parentheses, how to compute this product. So one way is, I guess, this. Then from here, we can go with gamma AB, comma C, comma D. So like AB is a single object now. We can rebracket things. And so what we get is AB, CD. Is it okay that we get this? I mean, it's okay, just why would I care, right? That's the real question. Well, let me care anyway. And say I want to get to a place where everything is more bracketed on from the right. Here we started from the left. Let's get to where it's on the right. I can get from here there. So it's something like A, B, C, D. So what is the idea? Now we shall use this CD as a single object. So it's like gamma A, B, C, D. That's the thing. But we can get to the same new parenthesization by some other route. So we can go, we just make it within this triple in this group. So we will keep this guy. So it's A, B, C, D. Now, who is the morphism which is written here? So you see, it's just happening for A, B, C. So the thing is, it's gamma A, B, C. But then this D is not touched. So what is the political correct way of writing it? I should take it's this morphism, but now tensor with identity there. So here I will write that tensor thingy. So the one that I'm omitting here because it's just way too much. But here it would be confusing not to write it, so I'll just write it. Tensor 1, the identity on D. And don't worry, very soon I will stop writing all those morphisms, just keep writing those arrows. Okay, now from here, we're trying to move it to everything to the right. So we can go to A, B, C, D. What's the trick? The trick is to understand BC as a single object, right? So it's gamma A, B, C, D. And now you see that from here to there, we just get it with a singular parenthesization for the last three things. So this is gamma B, C, D, and answer identity on A. So this is the simplest example where one can see two different ways how to get from the same, have to get from something to something, just using gammas. If I use more objects, then there will be many other ways how to get it. Here there is just one, say, single cycle. If we invert those things, then we get back with a cycle. And the thing that we demand is that this guy, this pentagon diagram, is commutative. So such that the pentagon such as this thing. And this pentagon is going to haunt us for some time. So, okay, well, but what to do? At least it will get smaller and smaller, and those letters will start dropping from it. So maybe it will not so bad. There is still one more thing I should add. There should be also a unit. So let me tell what's happening with the unit, even though we're going to largely ignore this thing with unit. So it's this. So this is the pentagon. Together. With an object 1 in C and isomorphisms, natural isomorphisms. Natural isomorphisms from one tensor A tensor 1 such that what one needs is, so we might imagine that if you have A, 1, B, this thing, there are two ways how to compute this product. Either I can directly use this isomorphism here, so this becomes isomorphic to A, so it's just product of A with B, or I can re-bracket things, get to A, 1, B, and now we use the isomorphism between 1 times B, and tensor it with identity over A, so such that this commutes. Okay, now that's the definition. It's pretty long in some sense. Just to tell you what is going to happen now. As I told you, I will not concentrate too much on this unit. Basically, I will pretend that the unit is strict, if you wish. Or just we simply pretend that one tensor A is just equal to A, and is just equal to A tensor 1 whenever it's really needed, though it's not really politically correct. But this part we're going to really explode in some sense. Now, one reasonable question is, why do I write this axiom just for the pentagon, just for those 4 objects, when if I wrote, say, 5 objects, A, B, C, D, E, there would be way more ways how to parenthesize this product, and there would be many more of those elementary arrows. One would get some huge graph of things, and we should still, probably to make it reasonable, we should still demand that this thing is commutative.
MacLane's coherence theorem.
Yeah, exactly. Now there is this MacLane's coherence theorem that I'm going to write down. So I sort of imagine that you heard all that stuff. If you want me to skip it, I'm very happy to skip it. But I will just, okay. Since if you don't want me to skip it, then I'm very unhappy to non-skip it. Okay, now there is this theorem, which is called well, it's due to MacLane, or it's called MacLane's coherence. Theorem, and it's there are several ways how to say it. I will just say it in some reasonably naive way, which just says that that all the isomorphisms obtained by composing gammas are equal. That's the theorem. So not just for 4 objects, but for arbitrary number of objects. When you start to reparenthesize things using those gammas, you start writing things like this. You will always obtain commutative diagram, provided those pentagons are commutative. And before going to the proof, let's try to visualize just to see what we're going to prove. Then say if I'm mean enough, but not on Florian because he's going away, but so on his replacement, I'll put some direct categorical and easy and short proof to the exercises. But here I will tell you, maybe with a little gap, some indirect, geometrical, and long proof, but which is sort of nicer. So before going to this proof, let's start with some visualization. just to see what we're going to prove and what we're talking about. So first of all, I want to understand, I want to have some visualization of those parenthesizations. So if you have, say, I don't know, 5 letters, A, B, C, D, E, let's do some parenthesization like this. So one way how to visualize it with a planar binary tree. So one way how to do it, see, like here we have AB, A is joined with B. Right, from this side there is this D and E. They are joined. Now they're multiplied with C from this side. Oops, sorry. And finally, here is the output, and I will put there a star for the output. It's just going to be some special letter for the output. So just imagine this kind of trivalent trees in the plane. They are in the plane so that we know what is the order of those objects. So say the simplest thing would be probably ABC, this thingy. That would be, this would be what? Something like A, B, C, star, that thing. And now A, B, C. That thing would look like A star, B, C. So now you see, when we look at that gamma thingy, gamma happening between these two, A, B, C. So what is doing some sort of flip here, that you take some internal edge, one edge, and it's being replaced with an edge that looks like this. Let me try a different visualization, which is possibly easier in some sense, but it's just dual to this one. It's still geometrical. We just draw a dual thing to this thing. So it's 1, 2, 3, 4, 5. So let me try the same thing. So there are 6 letters altogether. A, B, C, D, E, star. And now A is multiplied with, if we go from like this, A is multiplied with B. Now D with E, and now this DE thing is multiplied with C. That's the thing. And how it fits with this first visualization, you just draw the dual graph to this thingy. Okay, so that's another way how to visualize things. Just always this, when I draw a diagonal, it means that those things that are incoming, they are multiplied. Right? So here like this, D is multiplied with E, and now there is another diagonal which says that this product of this product D is multiplied with C. And in this language, what is this simplest thingy? It's like A, B, C, A, B, C, star. And when we have first multiplication of A with B is this, and when first multiplication of B with C is this. So this is what gamma A, B, C does. So what it does, it simply takes a quadrangle somewhere inside, like two adjacent triangles, and it removes this common side and replaces with a side like that. So let me draw what the pentagon is. This thing is, so I'm going to erase it and write it again. So that pentagon diagram, we should have some pentagons, I imagine. Okay, that's the difficult part of to draw pentagons. Okay, so what is the labeling? Labeling is like A, B, C, D, and star. It's the same labeling on each of those pentagons. Now, how should I, if I want to have there this, everything parenthesized from the left, A, B, C, D, this thing. So how should I draw those diagonals here? Yeah, I should like A with B, and then the outcome should be now multiply with C. Like this. Okay, and now what we can do is just to have the same order. Okay, I will have the same order if I go from here to there. How? I will just forget about this triangle. I will concentrate on this thingy, on these two triangles, and there I do the flip. I do the flip here. And now, like, the fate of the thing is decided, right? Like, if I did the flip here, I shouldn't do it again because otherwise I go back home. So I have to do the flip here. Okay, now here I should do the flip with the opposite side. And here I should do the flip here, I guess. Okay. So the pentagon identity says that this commutes, that when we do these kind of things, then it commutes. But we actually know a little bit more that some other things also commute, even though it was not written there. It just commute automatically. So there is some kind of statement that if you have, say, whatever, we have two of those quadrilaterals, which are disjoint in the sense that they have disjoint unions. They can touch. I mean, they can have a join side, but so it's all happening within one big polygon that we have two of those quadrilaterals, and now say they are, of course, divided somehow. We have triangulation, so that we have those triangles inside. And now, an obvious thing that should happen, and that happens, that it doesn't matter in which order you flip. Whether you flip first here and then flip there, or whether you flip first there and there. Okay, so flips in disjoint quadrilaterals commute. By disjoint, I mean disjoint interiors. And why is it that they commute? There are actually even two reasons. I mean, that there are two different situations when they commute. Because what might happen is, say, let's imagine that we have something like this: A, B, C, and times B, D, E. That's a situation like this. So we can do the flip here, or we can do the flip here, and they commute these things. And why would they commute?
Because it's more or less the same map, because you just tensor.
Yeah, exactly. So what's really happening here, that if we take like gamma A, B, C, tensor with identity on this nonsense, okay, B, D, E, something. So if we say first do it here, and then we do it here. Now it's the stupid rule of composing from the other side. So what I would do, I would keep identity here and tensored with this guy. So it's like identity of A, B, C, some whatever is the thing, tensored with gamma B, D, E. And now it doesn't matter which way you write it, because like by composition means that we should compose this with that and this with that. So we're always composing identity with somebody. So it doesn't matter whether we compose it on the left or on the right. So that's somehow, just using gamma on two disjoint groups, it doesn't matter in which order you perform it. But it might happen, so this is one possibility, it might also happen that those two groups are nested. So what is the corresponding thing to this? What's happening here? That here we have our star, then there is this polygon. And those, you see, those flips always concern some particular diagonal. We take a diagonal, look at those two surrounding triangles and replace it with the opposite diagonal. So this happens when we have somehow two diagonals which are somehow in this kind of position, that star is away. That you can see the star by looking from each of those diagonals. That's the situation here. Then we have two disjoint groups. They don't talk to each other. But it might happen. This is not the only possibility how to have diagonals. The other possibility is that one will obstruct the view for the other. So one will not see the star. So we have like star, some polygon, and it might happen that here is one of those diagonals that you're going to flip, and there is some other diagonal that you're going to flip. So what is the situation here? The situation here is that you have something like A, B, C, which might be happening somewhere here inside. And now you want to see, maybe together with many other things, as a single object, and want to re-bracket it with, I don't know, with D, E. So what you can do, as I said, you can view this thing as a single object. It is a single object. So in principle, there is a gamma which will send it to A, B, C, and D, E, this way. Right? The object as itself, as it is, it will stay. But then what we can do, we can reparenthesize that inner group. So we can do something like A, B, C, and D, E. Or we can first reparenthesize the inner group A, B, C, D, E off, and finally go here. And it still commutes. Now, why does this commute? It's all just some stupid categorical nonsense. So
It's naturally gamma. Naturally gamma.
yeah, exactly. The gamma is a natural transformation. So we just will commute with any morphism. It's in particular also with some other gamma. There are no other morphisms that we're using here besides gamma, so it's just by naturality. Of gamma. Maybe those things are easier to visualize when we talk in terms of those graphs. So in terms of those graphs, what's happening here? There is this root of the thing, and now it starts spreading. And we just simply do the, say, for example, we use this edge for the flip. So something is happening in one group, and say we use this edge for the flip. So something is happening in some other group. Those are those two groups that appeared here. They are nice separate. They come in a product. Or it might happen that they are one after another. So they are nested. This nested possibility is that okay, something's happening. Then maybe we make a flip here, and then we make a flip again here. So to go from, if you go from the root to one of those edges, you need to pass through the other one. So that's what corresponds to a nested thingy. Okay, but now it becomes very combinatorial or geometrical or whatever. Let's just suppose that we take a polygon, and we choose a triangulation. We just choose enough of those diagonals so that it's split into triangles. And we can start doing operations that whenever you choose one of those diagonals, you can flip it. The thing. And we have rules that if you do it within a pentagon, so if you take somehow 3 adjacent triangles and we go through a cycle, that we get something which is identity. And that when we take 4 of the 4 triangles, that's what's happening here, and flip it here or flip it there, that this thing commutes. And we want to prove that just these 2 commutativity rules, they imply that everything commutes. What time is it? So let me, before the break, let me reformulate in this way. That we're going to consider some groupoid. Groupoid, I don't know if you know the terminology, at least here is a category where all morphisms are isomorphisms, so where everything is invertible. And now we consider some particular groupoid. So our groupoid, we choose take a whatever n gon. Now, and we construct some groupoid with objects, split into triangles. Okay, triangulation. So for each n, if you wish, we're constructing some silly groupoid whose objects are all those possible triangulations of whatever regular n-gon. And now morphisms are generated by flips. This means that for any flip, we say that we have some particular morphism going from the first configuration to the second configuration, from first triangulation to the second triangulation. And generated by means that we can now start formally composing those flips. There are no relations yet, so this would be like a huge thing where automorphisms group would be some free groups. But now modular relations modulo the pentagon and the two tetragons relations. So the relations that if you have a pentagon and go around that, we get identity, and that when we have 4 different triangles that form 2 of those tetragons, then those 2 flips commute. And the statement should be, the statement of this Maclaurin's coherence theorem is now that for any 2 objects, there is a unique morphism, meaning that this groupoid or this category is sort of trivial in the sense that any 2 objects are isomorphic, and its isomorphism is just unique. There is no other morphism between them. So in some sense, everybody is canonically equal to everybody else, except it's not really equal, it's just canonically isomorphic. But to see how to get this result using some cell complex, it will be after the break. Yeah, so you're actually better behaved than analysis 1 students, because there was this silence without me saying anything. Okay, so here, this was the statement that we're flipping those diagonals in some triangulation of some polygon. We suppose that there are some elementary commutativity things, and from that we should see that everything commutes. And it is really a sort of combinatorial statement. You can also prove it combinatorially, but let me give you some geometrical proof, even though there is going to be 1 gap. But it's a small gap. If I didn't tell you, you wouldn't notice, or maybe you would. The idea is to construct some cell complex. But first I will tell you what kind of space it is, and only then I will tell you what the cells are. So the space is going to be obtained from cubes by gluing those cubes along their faces. But those cubes are not going to be our cells. Those cubes are just too small. We want somehow bigger cells, larger cells. So, and what kind of things I'm talking about? Just imagine we have one of those. Well, we have the polygon. Now some triangulation. Whichever. So those would be, that would be an object in our groupoid in the end. But now I decide how thick I'm actually drawing those diagonals. So some of them are with full thickness, and some of them are just a little bit faded. I guess it's already happening here, but I don't know which is, let's say, this one is going to be really thin. So what's happening here that for any, it's a triangulation, okay. Plus a number from interval 0, 1 on chosen for on every diagonal. So some of them might, for some of them it might be 1, for some of them it might be 1/2. And for some of them, it might be even 0. So what kind of, for a given triangulation, what we have here is a cube, right? So like for each edge, or sorry, each diagonal, we're choosing a number. So this for a given triangulation. We have something like 0, 1, to the power of those diagonals, a set of diagonals. In other words, a cube. And now we will glue those cubes, and there is a reasonably obvious way how to do it, because I told you, you should imagine the number of, which means how thick I'm making the diagonal. If that number is 0, it sort of means that the diagonal is not really there. So that's how we identify things. So it means things are identified only when you have somewhere 0. And it simply means that you erase the diagonal. And if you see the same picture, you just identify it. That means probably that the full space is that you take all subdivisions of the n-gon bidiagonals, and not necessarily triangulation. So we don't need to divide it completely. We might leave out one of those, so not necessarily. Necessarily triangulations. With a number from 0, 1 on each used diagonal, and plus identifications which simply means that diagonal, a diagonal with 0 is identified with no diagonal. Is this thing. Now let's try some, say, the simplest example.
So subdivision here also means that diagonals can't cross.
Yeah, they cannot cross. They are not allowed to cross. We don't necessarily divide it completely. So let me try some of the simplest example, which will to make sense of what's happening here. Let me take it for 4 sides. So the thing that we might, there are 2 possibilities for having a diagonal. Either this one or that one. And what is the space that I'm talking about? You see, you can put here a number from, say, let's start at 1 and go to 0. So it will be like this is some kind of limit point. This is and here in the middle is the configuration when that's the thing that we're gluing. That's when there is no diagonal, or if you imagine diagonal with 0, but it's the same as this diagonal with 0. So there we get somehow just an edge. So a segment. That's the space where our space and the space I'm talking about for the case of 4-sided polygon is simply a segment. Say of n-gon. So this thing is chosen. That's the same n that we have here. So here for n equal to 4, we have a segment. That's the space. I guess it's okay. Now, for n equal to equal to 5, the thing is somewhat trickier to draw, but let me try. The outcome is going to be a pentagon. It's a little bit of coincidence. You see, here for 4 we have a segment, so the fact that for 5 we have pentagon is 5 and 5, you shouldn't take it too seriously. Otherwise you get horribly confused. So the space that we get there is really a pentagon, and there will be many pentagons around. And now, so what are those extremal things here? What are these vertices? As it was here, that means that we actually have a triangulation and everybody is fully drawn. For each of those diagonals, we put there 1, like full weight. So there would be things where I would again be drawing pentagons, but it's not this pentagon, it just happens to be again a pentagon. So like thing like, for example, I don't know, like this. This might be what's happening here, right? And what's happening here, that should be the same thing, but with a single flip. So let me flip, say. Maybe I'm using it differently than before. Don't worry. And there are those 3 other possibilities around. And now, you see, let's see just what is happening on this edge. The part which is connecting this with that. So what's happening there? It will be just what you're seeing here. Well, let me just ignore the part which is not being flipped. So here in the middle, we shall have again a pentagon. Well, this part is not being flipped. We put here some other is 1, 1, 1, 1. Here there would be, sorry, there is 1. All the time there is 1. Just here, as we go this way, this edge starts fading away until it completely disappears, until it comes to 0. So let me just not draw anything. If you wish, I can draw it like say this way, but with 0. It is the same if I draw it that way and with 0. Those 2 things are identified. So that's what's happening in the middle. Here somewhere, this edge is 0.5 when we go somewhere in between. So that's what's happening here. And now there is a similar thing happening over here. And what we should finally see, you see, let me take the center of the pentagon, and let me take this part of the pentagon. It happens to be a square, topologically at least. It's a square. And what it corresponds to, it's like what's happening at this edge. So what's happening at this vertex. It's just, we have exactly this configuration, but with arbitrary weights. That's what's happening in this region. When we're on the boundary of the region, it might happen that somebody goes to 0. That somebody goes to 0 exactly here. That's on 1 diagonal when we have 0. On this part is the idle diagonal that becomes 0. And in this point, it's both diagonals that become 0. And you see now the combinatorics of the thing somehow is actually split into 4 of those tetragons. So, sorry, 4 to 5, sorry. For each of those configurations, we have something like that. And when they meet, it means exactly that one of those weights is equal to 0, so they can meet. Or here, all of them meet, because then when both weights are equal to 0, here we simply have empty pentagon with no subdivision. So that's what's happening. Okay, now what can you say about this space? Well, it's given by certainly some cell decomposition into cubes. It's a cubical complex. But as I said, I don't really want to use this subdivision because there are all kinds of strange points then, like these, all these points. I only want to keep these, like those full weights, when all those weights on all those diagonals are equal to 1, and every diagonal, and Like we have a full division to something, we have a triangulation. That's the thing that is interesting for me. But still, let me say something. Certainly the space, so this is certainly contractible. How would we go about contracting it? Just say multiply all those numbers with some t and go with t from 0 to 1. You'll get a wonderful contraction. No problem. But actually, and this is the part where I'm cheating, where one needs to verify. It's not just contractible, it's very nice. It's actually, it's topologically, it's a cell. I mean, it's homomorphic to a ball. And if you want to know more about this, or possibly you heard about this, you know that it's a beautiful story, those things can are very nicely realized as just some kind of complex polytopes, as it's here, this pentagon is one of those, and this is called those, it's called an associahedron. For each n, there is a particular associahedron. This is just this space.
So is it something nice for n equals 6? Like something that...
Yeah, something very nice.
What is it?
I don't... It's something, yeah, it's something really nice. No, and okay, it's something three-dimensional, and which has either squares or pentagons as faces. And it's not very regular.
Okay.
And in any reasonable mass department, you would find a model.
Okay.
This might mean that this is not a reasonable mass department, I'm not sure. Okay, so I just got myself fired, so let's go. Let's go on. So what? Now we shall need some self-decomposition. Of our space. Well, you know, if in reality this space is some convex polytope, then this cell decomposition, we're just talking about faces of all kind of dimensions of this polytope. But let me be like precise without knowing that stuff. What we shall do? Let's take, how to put it? So it's the choose sum. And non-intersecting diagonals and put their weight 1. And the part of the space which is obtained in this way, so say we have, for example, like this. Let me take one of those pentagons. I'll just say that I impose that here is 1, but I don't impose anything else. I'll just take the part of the space which is given by the fact that there is this particular diagonal with weight 1. So which part of the space it is? I mean, we can either have this diagonal with some weight, or it might become 0, or we can have this particular diagonal with some weight. So what do we get in this picture? In this picture, so it's turned a little bit, whatever, we just get one of the sides of this pentagon, in this case. And what does it look like, this kind of thing? This, in fact, it is a product of several of these associahedra of several, say, our spaces. well, for different ends. Do you see it? Like, let me say, make some bigger example. Let's say choose this guy and I don't know this guy. These have weight 1. These have weight 1. So what you see now, like this thing is split into 3 polygons, and inside of each of those polygons you can put arbitrary weights on. See, so here we have our space for this n-gon, here for this n-gon, here for that n-gon. So it's just product of 3, in this case of 3 of our spaces. But the only thing that I need to know that if those spaces were balls, then their product is again a ball. So we can somehow understand it as cells. And this gives us so this is a cellular decomposition. So you see what's happening, roughly speaking, that when we take the full thing, so that means we don't impose any one anywhere, you get the interior of the thing. Oh, we just get the full thing. Then when we impose it on just for one diagonal, then we get a cell of codimension 1. We just impose one of those parameters to be equal to 1. Everybody else can vary as it is. So the dimension is just decreases by 1. When we impose 2 of those things to be 1, we get something of codimension 2, etc. Okay. So codimension is equal to the number of imposed ones. And okay, so here we are, and now finally we go to compute the fundamental group, or if you wish, fundamental groupoid of our space. Well, we know that this fundamental group is not very interesting if the space is contractible, or if it's a ball. So pi 1 is just whatever, 0 or 1, because we have a contractible space. But let me now talk about the fundamental. Let's look at the fundamental groupoid. With a base set where objects are just triangulations. Meaning that there are points in our space with weights equal to 1. So why am I using these points? Because they are exactly cells of dimension 0. Right? So these are the same as cells of dimension 0. Why is it? Well, to get dimension 0, we have to impose, we just have to fix all parameters. That means that we impose enough of those ones that there are no numbers left to be moved. So we choose a triangulation and impose that everybody is equal to 1, all those parameters. That's again a cell, which is 0-dimensional. Those are exactly our points. And now, how does one compute the fundamental groupoid of using some cell decomposition? Well, we have those objects, which are those 0-dimensional cells. Then there are generators, which are given by 1-dimensional cells, so things connecting those 0-dimensional things. And then there are relations given by 2-dimensional things. But what are exactly those 2-dimensional things? Okay. Okay, so objects, 0 cells. Now generators of morphisms are those one-dimensional cells, and relations are two-dimensional cells. And finally, here we are. What are those two-dimensional cells? Two-dimensional, that's when do we have something two-dimensional? That's when we have just two parameters that can change. That is, that we fix like enough of those diagonals that there might be just two remaining there where we can play something. So there are two kinds of those two cells. Either our incomplete triangulation, our subdivision looks like that there is some pentagon inside without any imposed labeling. So this is one possibility. Or there are two quadrilaterals. There are those two possibilities. So the relations are exactly this: pentagon and then commutativity of two disjoint flips. That's what he wanted to show, right? The fundamental group weight was supposed to be like trivial in the sense that between any 2 points there is a unique path up to homotopy. We're on a ball, so sure that this is true. And we just understand we can build the same thing just by looking at these. Well, we know the objects, but just by looking at those generators and these relations of this kind and of this kind. That's it. So let me draw one more of those polygons and call it the end of the proof. Okay. Now, I still keep the title braided monoidal category, so maybe let me use this title. So what is a braided monoidal category? How to put it? I'll start in a somewhat simpler way because, say, the moral of this theorem that we just proved is that you can always pretend that your monoidal category is strict. Say, when nobody's looking, you are free to remove all those parentheses and just compute with those products as they are strictly associative. Everything is going to be fine. Only when all of a sudden somebody comes and starts looking over your shoulder, you should quickly put there all those gammas and things like that, but everything is going to work. Everything is fine. So let me now tell you what would be braiding in a strict monoidal category, and then let's work back in those gammas. So say a little definition, a braiding in a strict monoidal category C is, so what is it, or what is the, why we are caring about it? You see, in this category like sets or in vector spaces, there this product is sort of commutative. You can say that x times y, well, it's not really equal to y times x again, but it's always canonically isomorphic to that stuff. So we're going to have something similar here, but in the case of categories, one can have some weaker type of commutativity, and that's really like possibly the main part of this course. Braiding is going to be important. So what is this braiding? So it's a natural isomorphism between AB and BA. So let's call it like beta AB. So what it really is, you see beta is a natural isomorphism between when he will just do, say, flip, go to C times C, and then we compute the product, and beta is an isomorphism like this. And such that, and here there is one little trick which is entering. You see, Ines, what would be in the end symmetric monoidal categories, or a thing that you probably met in some sense. If you exchange two things and exchange again, you get back home, you get identity. And we're not going to require that thing here. But we're still going to require something. We require that if we jump, say, we can jump with A over two objects in two ways. We can either jump one by one, or we can jump over their product in one term. So there are two ways. So jumping like this, and this should be the same as taking A and jumping over BC in one turn. What does it really mean? So what is it? It's like beta AB, and I don't touch C, so tensor identity on C, composed with, now it's identity on B, tensor, and I jump with A through C. And this thing should be the same as beta A comma BC. This is the requirement. This is one of them. And because I'm not supposing that doing beta twice will turn me home, then there is another way how to jump over things. BC is equal to ABC, where we do jumps like that. What does this jump mean? Doing jump like that is interpreted as by definition when you have AB and you jump with, you take the inverse of jumping with B. That is, this is beta BA inverse. It's like the same kind of diagram, but where you use those inverses. Okay, now this was in a strict monoidal category. Now in a true monoidal category, what would happen? So definition, I braided monoidal category. So is a monoidal category with this beta. Exactly. As in here, and such that these two things are satisfied, but where we need sometimes to re-bracket things. That, what is it? 1 and 2. Hold with enough of gammas put in. So wherever you see, we need to use those parentheses and we can put those gammas. Let me now, should I even use the paper? Yeah, I probably should, but I didn't write it on the paper. So. Or maybe I did. Okay, so let me tell you what it actually means, at least for one of those. For one, what this thing becomes, and for two, I can leave it up to you to put there those beta inverses. So that is that we have the following thing. See, let's take A, B, C, and we need to choose some parenthesization. And let's say that I want to jump with A over both of those two things. I cannot do it right away because they should be parenthesized, so there should be a single object so that I can jump over them. So I need to use a gamma. I will leave it up to you to write what kind of indices one needs to use here. So we get to A, B, C, and just yet I'm using this wonderful trick of putting there a diagonal. And then we can use beta to jump with A through this BC. So we can go to BC, A, and let me land in BCA, where parentheses like this. Or I can jump with A already. So here I'm using beta, but it's really like beta tensor identity on C. So it's BAC. Then I want to jump still through C, but for that I need to combine A and C. So I need to put here some gamma, and it becomes BAC like this. And now inside this group, I can take the identity on B tensor beta on those two things. Beta. So this thing should commute. So this is what is called a hexagon. Hexagon identity, and there are two of them, because there is one like this and the other like that. Okay. And now, how does one draw things, or anyway, why it's called braided monoidal category? So how to draw those things? Let me now for a moment forget about those gammas, because we know that they are somehow not really, we can always forget about them. And only when really needed, we always add them into the picture, and there is no problem. So the drawing is that or representation, graphical representation of things, is that I'm going to draw the morphisms from bottom to top. That probably comes from my past of being a physicist, and where in space-time things go that way. Just happens this. Yeah, that's the explanation for things. So A, B, sorry, this B is too long. B, A. So this kind of thing, that's what is beta AB. So we're going to represent it with this kind of single crossing. And so now, when we start using those gammas, so using those betas arbitrarily, you can have something like, A, B, C, D, and here, I know, B, C, D, A, and let's start using them, and yeah, I need to, this guy goes here, this guy will go here, this guy might, whatever, do something like this, and this one might goes behind, yeah, I don't know, and do something of the sort. So we can start drawing these kind of things. But does it make any sense? Yes, it does, because now there is a wonderful theorem which says that that a morphism obtained by composing, or any morphism, by composing betas depends only on the resulting braid. Which literally means that you see I start composing betas, just do those elementary crossings, obtain some braid. But now when I deform this braid, obtain like the same braid, but just moving those strands in some other positions, I get some composition of different betas. And the statement is that we get the same result. This new composition is the same as the old composition. And why is it true? You know, what we have here, these betas or their representations, this is what corresponds to those Artin's generators of the braid group, right? Just those elementary crossings. So we need to verify that these betas satisfy Artin's relations. That's what we need to do. Now, what were those relations? There are two types of relations. One is sort of easy-ish or easy-ish. One is this kind of that if you have 4 strands, then it doesn't matter whether we do the crossing between first and then between those two. So something like this. That this thing, and then followed by, maybe there are other strands between, and followed by this thing that is the same as this thing and that thing. So it would be like, so what is it? That we first apply beta here, I don't know, like beta, and there's again this stupid rule of composing from right to left. So I should do it like, I don't know, A, B, C, D. So it would be like beta, A, B, and keeping identity here, tensor with identity on CD. And then we compose it with, now with beta here and identity there. So it's identity on AB. No, it's not comma, it's times. Identity on AB tensor with beta on CD, this thingy. Identity on BA, right? We did here. They got flipped. BA. Composing with it this way, but it doesn't matter whether we do it that way or this way, because here we're composing beta with identity and another beta with identity. So their product is simply one beta tensored with the other beta. So it's just beta AB tensored with beta CD, and that's equal to the same thing in this position. Okay. The other thing. Okay, just this is equal to that because we can write both of them simply as this product. It's stupid. Okay. The other thing is slightly less stupid, but it's still very simple. So what is this other thing? The other write this other relation in this way. Okay. Let me do it like this, and here, okay, braiding, I probably should do it this way. This Artin's relation, well, written this one, just says that we can move this crossing to the other side. So it's a question mark whether it's satisfied, whether it's the same as having them like this and having then this crossing there. So like A, B, C, A, B, C. So is it true? Or say, for people who don't know whether it's true, so is it true? It is true. And why is it true? Because beta is a natural transformation. You see, with like taking beta of what's happening here, this thing is beta of A with BC. Is the same. What's really happening? You see, we're somehow using not so secretly that hexagon or triangle relation, that jumping over two things at the same time is just immediately replaced on those drawings with jumping over one and jumping over the second one. I don't have different drawings for jumping in one step over two things on jumping in over first one over second one. They're just equal, those two things. So I just represent it this way. But what this thing really is, or here, you see, I'm jumping with, this thing up to here is like this beta A and jumping over BC. That's what's happening. And you see, what is really just happening, that we're using naturality of beta. So by beta is a natural transformation, so it's going to commute with any morphism which might be applied on one of those sides. Here I'm applying morphism which is happening here. Which one is it? It's beta BC. Yeah, so it commutes with a morphism which just happens along this strand. Like the same thing would happen when we simply have A and whomever, something BC, whatever, D. Apply any morphism, doesn't matter which one, and go to E. This would be equal to, sorry, this is the, apply arbitrary, the same morphism, and go to E, A. So this thing is just true for any morphism, in particular for beta, and that's all. That's all that there was to prove. Okay, I should stop. So one can also ask, okay, so we showed that these things satisfy those Artin's relations, so it means that we always just see those braids. But one can ask, perhaps maybe they are like satisfy more relations. Maybe this is just artificial that I'm representing things by braids. In reality, maybe those corresponding groups are way smaller than pure braid groups that we would get by composing in an arbitrary braid monoidal category. But there will be some simple exercise where there is a particle of braid monoidal category which is already defined in terms of braids. And so you will see that the only relations that are ever satisfied there are those that are satisfied by braids. So in general, these betas are going to satisfy only those braided relations. So there is a good match between braided monoidal categories and braids. But that's all for today.